Swayam Prabha. Digital India. Educated India.
The problems that we just solved in the past several examples that you looked at, if you sort of think about how you did that. So you had the beam and the load, and you cut sections at the different points. This is the classical approach of drawing bending moment diagrams and shear force diagrams, or it is also known as the method of sections. And it is quite intuitive if you think about it. So if when you had the beam, you had the loads at different parts of the beam, you took the sections, and after that you wrote the equations for the shear force and the bending moment for the different sections. Then you went from establishing the equilibrium from left to right or right to left, whichever was convenient, and eventually from those equations that you derived, you drew the shear force diagram and bending moment diagram. Now, while this method is extremely intuitive because you can see and you know what you are doing, sometimes it can be very tedious. For example, suppose I give you a beam. So let's just go ahead and draw a beam. So suppose I give you a beam with maybe some boundary condition. So let's say this beam has a pin at one end and say a roller at the other end, and the beam say is subjected to a variety of loading. For example, so let's say the beam has a point load, has a uniformly distributed load, it has another point load, another point load. Here at this point maybe it has a couple over here. I can go ahead and maybe put another point load acting something like this over here, right? Maybe at the very end I have a little bit of a triangular load which is acting, and so on and so forth. I can go and make this problem as complicated as I can. Now for this problem, if you think of doing this using the traditional method of sections, where all would you have to take the sections in this case? You have to take the sections. You'll probably have to take one section here, another one just after this load ends, one over here, one right after this load, one in between this uniformly distributed load, one right after that here, one here, and maybe at the very end right after that moment x. So let's just do a count. I have 1 2 3 4 5 6 7 8, right? So total, to draw the bending moment and the shear force diagrams for a problem like this, you actually need to sit and write the equations of equilibrium for these 8 different sections, and that tells you how tedious this process becomes. Now, your saving grace for solving problems, these kinds of problems where you may have a more complicated type of loading than the one we saw, and which would require you to ideally find the bending moment and the shear forces at all these points of discontinuities in between the loads, within the loads, and so on. We are going to use a very efficient technique which is derived from the relationship between the load, the shear force, and the bending moment, right? Once we understand those relationships, you will see that how easy it becomes to draw shear force diagrams and bending moment. So let's go ahead and take a look what are the relationships between the load, the shear force, and the bending moment. We are going to look at the relationships between essentially three quantities. So we are going to look at the relationship between the load, say the distributed load W, the shear force V, and the bending moment M. How these guys are connected to each other. And we have, if you think about it, while we were solving the problems, we caught a glimpse of that. You remember the maximum bending moment was happening where the shear was going from the positive to the negative, essentially where it was crossing the zero line and so on. Now, although we have intuitively looked at that, now we'll look at it mathematically, that why those kinds of phenomena happen. So in total, we are going to look at primarily four different relationships when you have the distributed load and when you have the point loads and the point points. First, we look at the distributed load. That will give us two very important relationships, and after that we'll move into some special cases. So let's first take a look at the relationship between W, V, and M. That is the distributed load W, shear force, and the bending moment. Now for that, let's go ahead and first maybe draw a beam. So if we say have a beam here, right, and say let the say the beam has say support conditions, maybe one side is pinned. The relationships which we will derive are independent of the support conditions, but just for the sake of simplicity, let's assume that. And let's say on top of the beam you have a distributed load, so maybe something along, it's a thing along like this, where this entire load you are having a, and let this is a general function of w of x over here. This is the distributed load that we have, right? Now for this particular beam, and let's maybe mark the different ends of the beam. You have a over here, you have b over here. Now for this beam, if I separate a small chunk of say length delta x over here, so let's me call a point, let's say over here, let me call this C, and maybe another line over here which is C prime, right? And let's say that this distance that we take from C to C prime is delta x. Now if I separate out the C prime, what do we get? So if we separate out the C prime over here, we essentially get a small chunk of the beam. So here this is my C prime of, again, the length is delta x. On top of that I have this distributed load which is acting over here. So on top of this I have, so this is that w as a function of x over here. And maybe just for the sake of simplicity, if I take that section small enough, the load can be approximated roughly as a rectangular load, because that's the whole principle of integration that you do, that if you take it small enough, this load can be as you approximated as a rectangular load. So let's say just for the sake of simplicity, I represent this entire load maybe as an equivalent load with as a magnitude of w times delta x, right? So now that we have this section, we have separated this small section over here. Now this section, as you can tell, that from the, you have this the forces which are acting from the top, and also you must have the internal shear force and the internal bending moment, which is keeping everything in equilibrium. So let's go ahead and mark the internal shear forces and the internal shear force and the internal moment for this one. So again, I'm going to follow the positive convention that I have. So for when I am going from left to right, my shear force, I'm going to point it out as like this over here, and my moment will be like this. I will write the variable soon. And for the left hand side, I'm going to have this and this one over here. Let me maybe erase this arrow, we don't confuse what. So let's say that at the left end over here, my shear force is V and my bending moment is M. Now after you have traversed through this distance of delta x over here, due to this load, maybe the shear has changed by a little quantity. So let's say this one now is becomes V plus delta V, and your moment becomes M plus delta M. So I hope the system is clear. So what we did, we took a small chunk of that entire beam of length delta x, and here on the left end I have marked the shear as V and M. On this small chunk, this load is acting. As a consequence of that, when you reach towards that right hand side over here, my shear becomes a V plus delta V, and my moment becomes M plus delta M over here, right? So now let's look at the first two relationships which we are going to derive. So let me maybe divider over here, and let's look at the relationship number one. So relationship number one is going to be from the equilibrium of the vertical forces that we have. Now say in this beam, if say this is your, if you are taking your upward y, that's a positive y, and say this is positive x. Okay, I am just doing the equilibrium of the forces that is there, right? So if I am doing the equilibrium of the forces, what I have essentially is that my v, so just the forces, so not the moments, just I'm doing the Fy equals to 0. So we have V over here, and then you have the other force V plus delta V, and this is the last force that you have over here. So we have V minus V plus delta V minus W delta X becomes equals to 0 over here, right? So what do we get from here? From here, what we get essentially is that, you know, this V and this V cancels over here. So what you will essentially get at the, you know, after, you know, solving this one is your delta V, or the incremental change in shear that you get, divided by delta X equals to minus W. Now, as delta X tends to 0, you can say that, you know, it becomes the our differential equation. Then we get dv dx to W. This is a very important. What does this tell you? This tells you that the rate of change of shear is negative of the applied load. Now, mind you, very important point. This bears a negative sign over here because the W is acting vertically down. If W was acting vertically up, this would be a positive one over here. That's why when you take at this relationship in different books, in some books it's minus W, some books it's plus over here. So let's make a note of that one over here. But as you can tell, the magnitude is equal to the W that you get over. So let's make maybe a quick note. So the quick note is that what this tells you, magnitude of rate of change of shear is equal to the load at that point. This is what this tells you. Now, from this relationship that you have, remember what is dv dx? dv by dx is essentially, if you have a shear force diagram, the slope of the shear force diagram, because the shear force diagram that you draw, you have the v and then you have the x. Remember the shear force diagrams we drew was the, you know, the horizontal line is along the length of the beam, so along the x that you have over here. So dv is essentially the slope of the shear force diagram. Now, if I take this particular equation over here and if I, you know, integrate that, say maybe 2 points. So in this beam, suppose I have a point C, C prime, and maybe farther away I have, say, another point, say D over here. Okay? So if at a farther distance away I have, you know, a point D, then what I get over here is that if I integrate this equation which I just derived, that integral of dv dx, right, from say the distance. So if I'm measuring my x from, you know, this particular side, suppose I'm measuring my x this end, and say the distance to the point C is xc and the distance to the point D is xd. So what we have that from xc to xd over here, I will get negative of the integral from xc to xd of my w. So what that gives you is that the integration between these 2 points is nothing but the difference of the shear force that you will have at D and C. So what you get is another important relationship. So what you get over here is that your VD minus VC, VD is the shear force at the point D and VC is the shear force at the point C. VD minus VC equals to negative of integral xc to x of w. What does that mean? What is the integral of this loading diagram? And remember, this is all a function of x, so I should ideally write it as w of x function of. So what does that mean? So that means that, so this is another important relation. Get over here, make my box bigger. So what we get from this is that the difference of shear between 2 points is equal to negative of the area. So you see, this integral is essentially the area between between these 2 points C and D that you have over here of this loading diagram. So is a negative of the area of loading diagram between the same 2 points, between those, right? So what we just derived over here, that the slope of the shear force is equal to minus w times x, and your this vd minus vc is the negative of the area between those. That is our relationship 1. Now as you can tell, relationship 1 mostly relied upon the balancing of the shear, right? So now we have relationship 2, which you can guess which will rely on the balancing of the moment. So let's just try to write that as well. So if we have to write the relationship number 2, so that is the moment balance, that comes from the moment balance. So if I take the balance all the moments, so what I get over here is that my m plus delta m minus m, and if I am taking the moment about this particular point over here, it is minus v delta x plus w delta x because of this load that we have, times delta x over 2, 0. Now from here I get this m, and this m gets cancelled over here. This is very negligible because you are having a product of two very small quantities, so this can be neglected. Now after a little bit of rearranging, what we get over here is delta m divided by delta x to v. Again, as we did before in the limiting case when delta x tends to 0, so that gives you dm dx to v. This is another very important. So you see, the slope of the bending moment diagram, right, is equals to the shear, right? So now if you take the integral again, say between 2 points, so between C and D, what do I get? MD minus MC again. So if I take the integral, so I have, say, the integral between xc and xd. xc is the distance from here to the point C, and xd is the distance is from here to the point D over here, right? So from xd to xc, if I take dm x, I get integral of xc to xd of v, which eventually takes me to this relation, that is md minus mc is going to be what? What is the integral? And there will be a dx over, sorry, and there will be a dx in this relationship as well. Sorry, I that up. Let me just write bigger rectangle. Now coming back to here, you have what is this integral that we get, that is md minus mc is the integral of xc xd v dx. What does this mean? What is this quantity over here? This quantity is nothing but the area of the shear force diagram between these 2 points C and D, because you remember this variation of V with X is essentially my shear force diagram. So the integral between XC to XD is just the area of the shear force diagram between these 2 points. So essentially this takes you to another important relationship that you get over here, that the difference in moment between 2 points is equal to the area of shear force diagram between those two. So these are the first two relationships that we saw. So just to recapitulate, the slope of the shear force diagram, that is dv dx, is equals to negative of the loading diagram that you have over there, and the difference in shear between 2 points, right, that is the difference in shear between 2 points, say D and C, or any other 2 points, is the area of the loading diagram. This is as we wrote, is the area of the loading diagram between those same 2 points, xc to xd. The other relationship that we saw is that the slope of my bending moment diagram is equals to the shear, and the difference in the bending moment between 2 points D and C is nothing but the area of the shear force diagram between these 2 points. So these relationships are a little tricky to keep a track of, but once you just close your eyes and just try to think that what are these relationships, and try to have this ingrained in your mind, you will see drawing the shear force and the bending moment diagram becomes very easy. Now these two relationships are derived, or which gives the relationship between the W, see W and the V and the M. So between W and the V and the M, we have two more relationships, and those relationships are not for this distributed load but for a point load and a couple, and those are essentially takeaway messages. Not these are the relationships we are primarily going to use up, but those two other relationships which we'll see just now, which we'll name relationship 3 and 4, essentially helps you to keep a track of how some of the shear forces and the bending moment numbers would change when you encounter a point load or a point bending moment. Let's take a look at those two as well. Now, the relationships which we just looked at, if that small element had the distributed load acting on top of that. Let me just scroll up the page, show you. This is what we had looked at, right? But for the next two relationships, and this is not always the case, because you can have point load, you can have concentrated moment. So the next two relationships, that is relationship 3 and relationship 4, relates to the point load and the concentrated moment that we have. So let's take